chemical equilibrium now and Le Chatelier's principle. You did some reading last night in your book on chemical equilibrium, so you have a good basis for your understanding here. It's important that you write down all the notes that I have on the board here, and I'm going to use this diagram to explain about chemical equilibrium and how the concentrations remain constant. So reversible reactions at equilibrium have reactant and product concentrations that are constant. That means that the concentrations of the different substances remain the same. So I can see from this graph where the equilibrium point gets reached. Now at the beginning, when I mix my nitrogen with my hydrogen, I initially have a lot of nitrogen and hydrogen, and I've color-coded those for you right here. Initially I have a lot of nitrogen and hydrogen, and as these molecules bump into each other in the 1:3 ratio, they are going to form ammonia. And you see that the concentration of ammonia starts very low. So as these things bump into each other in the correct orientation with enough speed and in the proper ratio, we can make our ammonia gas, and that's going to increase until we reach the equilibrium point. So the point where all three of these concentrations level out, I can say that this would be the point at which the equilibrium was reached, and all the time after that, you'll notice that the concentrations do not change. They are remaining constant. The things that are equal in this system is the reaction rates, all right? So for every bunch of these molecules that combine, now I have two of them that separate. So for every time I do the forward reaction, I'm doing the reverse reaction at the same time, so that's how we get our dynamic equilibrium. It's not that we have the same molecules just sitting there not doing anything. Remember that they're gases and they're moving around and they're bumping into each other in the container. So they're going to continue to react, but it's going to go in both directions, the forward direction and the reverse direction. Okay? Once I have my equilibrium established, I can kind of play around with that. And you guys are going to do that in class tomorrow when I have a bunch of chemicals that you get to mix and play around with. So if a stress is applied to an equilibrium, the equilibrium will shift to relieve the stress. So we can predict how this equilibrium is going to change if I change the temperature, concentration, or pressure. So this is what you're going to be doing tomorrow. These two are pretty easy to change. The pressure one is going to involve mostly gases, right? Because gases are highly affected by changes in pressure. If I have a liquid or a solid, that's not going to really do much to shift our equilibrium. So if I have a system of gases, then I can change the pressure and see a change. Now remember that we're looking for observable changes, right? We're looking for changes in color. We're looking for precipitates to form, especially when we're dealing with solutions, right? Because if we have a saturated solution, I can get some to recrystallize, and that messes up the equilibrium. So if this is the example right here, I'm reacting two hydrogens with one oxygen molecule, then I will get two waters and the evolution of heat, right? This is the heat. So you can see from here that this is an exothermic reaction. That means that by changing the temperature, I can affect this equilibrium. I can make it go in the reverse direction faster or in the forward direction faster. Now in chemistry, generally we want to make more products. So if I wanted to make more products, what I would do is I would take some of this heat away. So if I lower the temperature, I am going to make more products. And what that means is I'm going to shift the equilibrium to the right. That shifts the equilibrium to the right-hand side. Okay? Now I like to use kind of teeter-totters to show this concept. So if I put this reaction on my teeter-totter and I take some weight off of this side, what's that going to do to this side on the teeter-totter? It's going to make it lower. If I take some weight off, it'll go up, right? So if I take some weight off, like if I had two people on this teeter-totter and then this person left, right, because the heat is over here. So if I lower the temperature, that's going to make this go up. Now to get it back to equal, which direction would I have to shift my equilibrium? Well, I would have to shift it to the right. So this is how you can tell which direction the equilibrium is shifting. If you are a visual person and you like to think about teeter-totters and, you know, the good old days when you were on the playground, you can use this teeter-totter to show you which direction the equilibrium will shift. Now what if I increase the temperature? What's that going to do to my teeter-totter? If If I added more weight to this side of the teeter-totter, which direction is it gonna go?
Cool.
It's gonna go down. If I add more weight to this side, that's gonna go down. And then which direction is the equilibrium gonna have to shift to relieve the stress? Left, okay? So the opposite is also true. If I increase the temperature, that's gonna make more reactants over there, and the equilibrium is gonna shift to the left. Now, for concentration, I can do the same thing. I can take a look at, if I added more molecules of hydrogen, now I have more hydrogen in the container that can bump into the oxygen, so of course that's going to make more products. All right, so increasing hydrogen will make more products because now they're bumping into each other more often. They're colliding, and so that's going to shift the equilibrium to the right. Now, if I did that the teeter-totter way, versus thinking about it, like if I added more hydrogen, then that's a higher concentration of a reactant, and I'm going to make more products from that. If I add more hydrogen, that's going to make my teeter-totter look like this, right? Because I added more weight to this side of the teeter-totter, and the equilibrium is going to have to shift to the right to relieve the stress. Okay? Now, what if I took oxygen away? What would my teeter-totter look like then? Which side would be up? If I took oxygen away, the left side would be high, right? I took some weight away from the left side. Now which direction would my equilibrium shift? To the left. My equilibrium would have to shift to replace the oxygen that I removed. Okay? Now notice that when we make a stress, we're doing something to the system. The system was already at equilibrium, it was a closed system, but now we're messing with it. Yes?
This is only for this reaction, right?
It's only for this reaction.
It could be subject to change for other reactions.
That's right. So you would just have to pay attention to what the reactants are and what the products are and where the heat is. Okay? So the heat being the temperature factor, and then the concentration would have to do with hydrogen, oxygen, or water.
Okay.
All right? And then pressure is the same for all of them. You can't use the teeter-totter. Pressure is dependent on the number of molecules on each side. Dependent on the number of molecules on each side of the arrow. Okay. So make sure you write that down. High pressure favors the side with fewer molecules. Okay, that's the rule. So if I increase the pressure on this system, that means that there would be less space available. There would be more bumping into each other, so I would have room for fewer molecules. Now right here, you can see that I have 2 hydrogens and 1 oxygen. So on this side of the reaction, I have 3 molecules. And on this side of the reaction, how many molecules are there? There's only 2, because this is heat, it's not a molecule. So if I had to increase the pressure on this system, which side would the equilibrium shift toward? To the right side, okay? So the equilibrium would shift to the right here under high pressure because I have fewer molecules over there, right? High pressure favors the side with fewer molecules. Now what's true of the opposite? What if I lowered the pressure? Which way would the equilibrium shift? Left, okay? So it's pretty simple when you follow these rules here, and again, this is just an example, so you'll have to pay attention to the exact reaction that you have and the conditions that you're under, okay? So tomorrow, when you come to class, we'll have some chemicals and you'll get to mix them together and shift their equilibrium. Okay?
Okay.